All right, good morning, everyone, and thanks, Michelle, for the introduction. I'm going to be talking about UMAP, which is short for Uniform Manifold Approximation and Projection. It's a dimension reduction technique, and we'll get into that as we go. Okay, so first of all, just a quick who am I? So I'm a research mathematician at the Tufts Institute for Mathematics and Computing. My PhD was in really, really pure math that I assure you do not care about. And these days, I'm trying to bring some of the things that I learned from that, topological techniques, to bear on unsupervised learning problems. So I have some great colleagues at the Tufts Institute. I'm a mathematician, and they are the people, John Healy, he's in the audience, he's sitting there. They're the people that know more about machine learning, and they help guide some of my crazy ideas. Okay, so first of all, what is dimension reduction? Let's just make sure we get everyone on the same page. So the goal here is to find sort of the latent features in your data. So why is this important? Well, feature engineering is important. Visualization matters. If you can get it down to 2 or 3 dimensions, you can look at your data. This is important. And often a lot of the dimensionality in your data is just redundant. And if you can prune that out, that can improve all sorts of other things, including further machine learning algorithms. So this should be familiar to you all by now. I think many other people have used the MNIST digits data set. So here it is, you know what it is. It's 784 dimensional though when you unfold those digits into long vectors. And we shouldn't really need 784 dimensions to describe a data point in this data set. There should be some much more compact representation. Here's fashion MNIST, which is a convenient drop-in replacement for MNIST where everything mostly works the same, but now it's pictures of fashion items, so bags, shoes, t-shirts, dresses, and so on. And so again, 784 dimensional, and this one's a little harder than MNIST, just so we have a little more challenge, but it feels like we should be able to compress that into a smaller number of dimensions and still get meaningful content out of it. So that's our goal with dimension reduction, is to take something that's very high dimensional, get it down to something that's easier to work with. So when it comes to dimension reduction, there's actually only really 2 techniques. There's matrix factorization or neighbor graphs. Now, depending on how you do that, all sorts of things pop out. Matrix factorization is everything from principal component analysis to word-to-vec and latent Dirichlet allocation. All depending on what matrix you try to factor, exactly how you define your loss. There's lots of details, but it's a whole slew of algorithms. Likewise, neighbor graphs, you get everything from ISOMAP to TSNE. These all basically build on the same basic infrastructure, and that's what counts. So PCA is the prototypical matrix factorization algorithm, and if we run PCA on MNIST digits, this is what we get. I've colored the points by the digit that they represent, and you can see it's actually captured a lot of the global structure there. The zeros and the ones are separated out, and there's a nice smear of different digits in the middle. The global structure is preserved pretty well, and the axes are interpretable. That's an important one for PCA. These are the directions of greatest variance in the data. All right. How about on fashion MNIST? We get a similar sort of thing. We've captured a lot of the global structure. We've separated out some of the groups to some extent. It looks good. So we're done, right? This is dimension reduction. Okay, there are other alternatives. What about the neighbor graph approach? So TSNE is kind of the state of the art in neighbor graph-based algorithms. And what does that do? Well, this is what it provides on MNIST. And you can see it's radically different than what PCA would supply you. Here we've captured local structure rather than global structure. But that means we've separated out all the digits really cleanly into nice little groups. Here's fashion MNIST with TSNE, and you can see, again, it's done a really great job of separating out the classes by looking at the local structure by building this local neighbor graph type approach. So that's how that goes. I want to talk about uniform manifold approximation and projection, though, which is my attempt to take the neighbor graph style approach and try and put it on some firm mathematical foundations, because the math side of things is what I'm interested in. So UMAP builds some mathematical theory in the background to really justify these graph-based approaches. I'm going to gloss over some of the fancier math. It's not actually hard, but it uses language that mathematicians might like, but a general audience maybe less so. So I'm just going to sort of try and give an intuitive description, and we'll just hide the math a little bit, but not too much. If you're interested in the math, come find me later. I'll be happy to talk about it in more detail. So first of all, we're going to do a little bit of math, a little bit of topological data analysis. I'm going to skim through this quickly, so bear with me. So the goal here of topological data analysis or topology in this sort of approach is that you can have these things that are simplices, which are nice, easy combinatorial representations of a bit of topological space. And the key is you get to glue them together into these complexes that can build, in practice, pretty much any topological space you care about. There are some pathological spaces, but they're not going to come up in data analysis. So the key here is that we can take something continuous and complicated like topology and turn it into something really simple and combinatorial with these simplicial complex type approaches. Okay, the next thing is a picture of a theorem. I don't expect you to read this. The guts of this is that there is some really solid math in the background from algebraic topology that basically says that if we build a simplicial complex out of a topological space in this certain way, we can actually recover all the important topology of that space. So we get to go from something complicated that's all continuous and topological to something simple and combinatorial that we can work with easily, and yet we retain all the information we want to care about. So let's look at an example in terms of data. Here's some data. It's on a hypothetical manifold. You can probably guess what the manifold looks like. And what we're going to do is try and build up this simplicial complex. So the goal is we start off by building a cover. And in this case, we're just going to drop open balls on each of the points. And that's going to cover our manifold. And then you take the nerve of the cover to get this simplicial complex. And here, this is what we get when we do that. The goal is pretty simple. A one simplex is formed by a pair of those open sets in the cover that overlap. If you have a triple intersection, you get a two simplex and on out. So again, simple combinatorial. It sounds too simplistic to work, but the math actually says this all does work very cleanly and nicely. And we've actually recovered a lot of the topology of the manifold there. It's not perfect, though. It has some gaps, it has some clumps. So what went wrong? Because we had this nice math theory that said this was going to work. Well, what went wrong was that the data was not uniformly distributed on the manifold, so the cover just wasn't good enough. If we go back to our cover, there are gaps because there are spaces where the data is more spread out and our open ball doesn't meet up with any others. If we have a nice uniform distribution like this, then you can see that this would kind of work perfectly and everything would look lovely and would get exactly the structure we want. So what we need is this uniform distribution assumption to make all the math work. But, when is real data ever that nicely behaved? But, hey, I'm a mathematician, so I actually just get to assume whatever I want. So I'm going to assume it's true. Great, we're done, right? This is case closed. Not quite. So the next catch is that if we assume the data is uniformly distributed on the manifold, that has practical implications for the manifold itself. Now, what that means is that we're going to have to define a Riemannian metric on the manifold that makes this assumption magically true. This is maybe slightly deeper math. If you're interested, we can talk about it later. But essentially what we're going to do is vary our notion of distance on a manifold. So here's a nice textbook picture of what manifold theory looks like. But the main thing that I want you to take away is that there's patches here that map down to nice standard Euclidean space. And you're going to have these patches all across glued together to make up your manifold. And effectively, what we are going to do is have these patches that map to Euclidean space on different scales, so that there's a different notion of distance, further or more compact, depending on which patch you're in. And that's effectively what's going on. Okay, so this is that data again, but this time I've used that approach, pushed through the math, and worked out what things should look like with this varying distance at each point on the manifold. And each of these balls is actually a single unit ball. They're all the same size as far as distance on the manifold is concerned. It's a different distance in the ambient space, in Euclidean space that we're looking at here, but according to the manifold that we're trying to claim the data lies on, these are all the same size. But why choose a fixed radius? I chose 1 there. Couldn't we have something that had a varying radius? In fact, we could sort of have the radius vary, and our confidence of how much in the set a point is kind of a fuzzy notion. Well, we could do that with something like fuzzy topology and pull that off. So let's do that and have a fuzzy cover. Now, the catch is making all that mathematically justified, because I sort of used a lot of vague words there. here's another picture of a theorem. You don't need to read or understand the theorem. The catch is that there is this nice theorem that actually defines how to do this in a really clean, simple mathematical way. It just uses a bit of classical algebraic topology and category theory to sort of glue the pieces together and make all of this work. So this is what we would end up with, at least in principle, some sort of fuzzy-like cover here, where the set sort of fades out as you get further away. Okay, we're going to need one more assumption, though. We're going to assume that the manifold is locally connected. Now, that doesn't mean that the whole manifold is connected, that there's only one piece. There's a whole bunch of pieces, potentially, but we are not allowed to have isolated points. The manifold can't have a point that is just completely isolated from everything else. And that's a very reasonable assumption to make from sort of a topological point of view. So what does it mean when we apply it here? Well, it's going to mean that we should be completely confident in our distance out to the first nearest neighbor, and then we can get fuzzy and decay from there. And again, we can use the math to make that all work out in practice. Why would we want to do this? Well, there's actually some side benefits here. So here's the distribution of distances to the 20 nearest neighbors for a set of data points, randomly selected on a normal distribution, in varying dimension spaces. So the catch here is that you can see as we go up in dimension, the sort of average or distribution of distances sort of slides out along that distance scale further and further. So the catch is if you go and normalize your distances in the high dimensional spaces, when we normalize everything back, our distributions get tighter and tighter and tighter. So in higher dimensional spaces, everything is approximately the same distance away. We don't have a nice smooth distribution of distances, we have pretty much just one distance. And this is the curse of dimensionality that people talk about a lot, or at least one major component of it. But if we take our local connectivity assumption and apply it, and then normalize, this is what we get. And actually, we've now got distributions that look nice. They look very much like the two-dimensional case. So it turns out that this local connectivity assumption, which was sort of a natural topological assumption to make, really helps us solve the curse of dimensionality problems. So great, we're done, right? We've solved all those problems. We missed one. All our local metrics are completely incompatible. So here's our nice theoretical picture of manifold theory again. And in the nice theoretical notion of a manifold, we have these maps at the bottom, tau alpha beta and tau beta alpha, that tell you how to go back and forth between the overlaps. We don't have those because we constructed everything from finite data. So we're missing all that information. So in practice, if we had our graph for our simplicial complex, if we could notionally do that, we'd end up with something more like this, where we have multiple edges between any pair of points with different weights on them because we had different notions of distances coming and going. How can we glue together all these different metric spaces to actually make a consistent picture to work with? Well, again, this is where the math comes back in. There's a nice theorem that you can prove that's not so bad that tells you that in practice we can just turn everything into fuzzy simplicial sets and we just get a whole family of them, one for each data point, and we can just glue them together by taking a fuzzy union. Now, what does that mean in practice for working with the graph? We're going to combine the weights of edges together under just this formula. And this looks a little weird at first as a thing to do, but if you think of it as the weight on an edge is the probability that that edge exists, then what we're really saying is we want the combined probability of the two different weights to be essentially the probability that either this edge exists or this edge exists. So the sum minus the product is really well justified in a probabilistic sense. Okay, so this is what we get out after all of that. It's a nice graph. If we ignore the higher dimensional simplices. And so we're good, but this is in particular a well theoretically justified graph. We know why we want to construct this particular graph in this particular way with these particular weights. So we're done, right? No, we need a low dimensional representation of this. Okay, so suppose we were given some low dimensional representation of the data. Well, we can apply the same process and get a fuzzy graph for that. But now it's a little different. Because this time around we know what the manifold is. I know if I want to embed the data in R2 in two-dimensional space. I know the manifold, it's R2. I don't have to try and infer the manifold. But we don't know this correct nearest neighbor distance for that local connectivity thing, so we're going to have to pass that in as a hyperparameter. Okay, so we can get two fuzzy graphs, and we can measure the distance between the graphs using cross entropy. And then if we just optimize, we get a layout in low dimensions that's going to solve our problem. So cross entropy looks something like this. But really, we're just doing a force-directed graph layout here. So you can think of this as the first term is kind of get the clumps right, which TS&E does. And you'll note that term looks a lot like the Kullback-Leibler term in TS&E. But then there's also this term, which is basically get the gaps right, get the gaps between the clumps sorted out. And so there's an attractive force and a repulsive force. This is kind of classical force-directed graph layout type thing. It's just a very particular formula that we derived purely from the math. So here's what the graph would be embedded like, and if we turn that into just points, this is what we would get. And that's great, but it's not quite perfect. We've got some jumps there. So what happened? Well, if you look at the original data, down in the green in the bottom right there, you can see there's areas that are just surprisingly dense, and our local approximation of density and things like that failed in that case because we just didn't have enough data. If we had more data, that sort of problem would be cleaned up more. So if we have more data on real data, what does it look like? So here's MNIST digits with UMAP, and you can see it gets the nice clean separation of the different digit classes the same way TS&E does, but it also has a lot of the spirit of PCA because of that get the gaps right term, where it spread the data out according to, spread the clumps out according to sort of more global structure. Similarly, fashion MNIST, again, much like TS&E, we've got the different classes all picked out nicely, but there's more understanding of the differences between the classes so that the shoes and footwear are all cleanly separated away rather than just being a clump mixed in with all the other clumps. Okay, so finally we're done, right? No, there's a lot of fancy math there. Can we actually make that into something practical? Okay, so yes, it turns out, because at the end of the day, what we actually need is a few things. One, we need to be able to find approximate nearest neighbors and do it very, very quickly, even in high-dimensional spaces. That's fine. There's random projection trees and nearest neighbor descent, and these are wonderful algorithms, and if you're not familiar with them, you should definitely look them up. They will do the job for us, and very efficiently. Then we need to do that optimization of the low-dimensional layout really quickly, subquadratically, ideally. Well, stochastic gradient descent and then stealing ideas from word2vec and large-viz, we can do negative sampling tricks to make this actually quite efficient. And as a side benefit, that allows us to embed into arbitrary spaces. TS&E only really works for 2 or 3 dimensions. Past that, the computational complexity gets pretty nasty. Here, we do just fine. All right, so it needs to be high level but still fast. How do I solve that problem? I'm a mathematician, not a programmer, so I'm not going to write something in C++ that gets all hairy. I will write it in Python, and then I'm going to make use of Number, which is a just-in-time compiler for Python down to LLVM to get the numeric side of it to go really, really fast. So just as an aside, Number is awesome, and if you're not using it, you should be. It produces high performance really, really well. The code you end up with is clean. It looks just like your standard Python code. You've just got a decorator at the top of it all, and it's got nice features. So it actually allowed me to implement custom distance metrics so that a user can define their own notion of distance, and as long as they can number JIT compile that function, they can pass it in, and with no loss in performance, everything runs perfectly. Okay, so how fast is it? Well, here's a comparison between TS&E, and this is multi-core TS&E. The TS&E implementation in sklearn is a bit slower, but not too much. And you can see UMAP runs a lot faster, and as you scale up in data size, the difference gets larger and larger. The Google News data set here that I'm talking about was 200,000 word vectors trained from the Google News. We tried all 3 million word vectors, and UMAP did that in a couple of hours. It took many days for TS&E to manage to do that. So if you want to scale up to really large data sets, we can do that too. Okay, but where next? we have this really nice mathematical foundation. There's really clean math behind all of this, and that actually opens up a whole bunch of opportunities to generalize this. So one of the things that we can do is we can embed new unseen points into an existing embedding. So here's fashion MNIST on the training set with UMAP, and then we took the test set and just added that to the existing embedding, and that works perfectly well. The advantage of this is it means you can use UMAP with standard sklearn pipelines. It's just the transform method. Everything works as normal. So you can just stick it in your standard machine learning pipeline as a generic dimension reduction technique. But we can do more. We can make use of labels and actually do supervised dimension reduction. So here's fashion MNIST where I gave UMAP the label information and it managed to make use of that. And now we actually fully cleanly separated the classes, which shouldn't be that surprising to you. We told the algorithm what the classes were, but the important thing is we actually retained all the internal structure of each of those classes, some of the stripy properties in the green and pale yellow clusters, and the overall global structure has also been retained when we do that. But we can combine those two things that I was just talking about and do a form of metric learning. So here's UMAP in supervised mode on the training set on the left and on the test set for fashion MNIST on the right. And you can see there's some confusion in the test set there, but for the most part, this has done a really nice job of actually learning a metric space that embeds new data really cleanly and understands the distances involved. We've retained all the internal structure of these clusters and the global structure as well. So if you compare that to something like triplet networks, this is triplet networks on fashion MNIST, you can see there's a similar level of confusion in the test set, but the understanding of the internal structure of those clusters is not the same. So there are some potential benefits here for metric learning as well. But adding one categorical variable, that label value, is actually no theoretically harder than adding many more. The theory actually makes this really clean and easy. We're just going to intersect with a bunch of extra fuzzy simplicial sets. So we can build fuzzy simplicial sets for any sets of distinct data types. So we can combine spaces that have different metrics. So if you have some continuous data and some categorical data and some ordinal data and some lat-long data that you want to measure with Haversine, if you have sparse enough data that you want to measure with Levenshtein, you can just have each of those work with UMAP with their own independent notion of distance, and we can fold them all together and embed them into one vector space. So as long as you can provide a metric for a data type for UMAP, we can, at least in principle, combine it with other data types. So what that means is, at least in theory, we can do UMAP for a generic pandas data frame. All right, so the code is available on GitHub. It's conda installable and pip installable, and there's still a lot more work to do, so if you're interested in helping out, please get in touch with me. Thank you.
My phone is telling you the talk is done. Thank you, that was a great talk. We'll take questions. Please ask only one question and phrase your question in the form of a question. I'm going to work this side of the room with the mic, and if you have questions on the left side, I'll call on you at the floor mic there. Hands up.
Is your approach easily scalable computationally, like just out of a core computation?
In principle, the algorithm is. In terms of my implementation, it is not. I was focused on proof of concept implementation, and so single core, non-distributed was the goal there. It would be a non-negligible amount of work to do a distributed version, but the algorithm has nothing in it that makes that impossible.
Oh, hi. Thank you. So I noticed on your graph of the sine wave shaped manifold, where you were illustrating the more spaced out thing with the larger set circles. One consequence of assuming the uniform manifold, or creating uniform manifold, was that the more spaced out things on the original manifold kind of got drawn together. So they ended up uniform on the new embedded manifold. So is that a bug or a feature?
I consider it a feature. People could consider it a bug if they were trying to do clustering and were worried about a lot of noise in their data. But actually, if you want to chat later, I have the same math that does this actually does clustering. You just turn everything around. If you're a category theorist, you can think of it as co-UMAP. It's just everything backwards.
Awesome. Thank you.
One more question. I just got one in front, so I'm going to go here and back.
Thank you. So I have a question. Is there some place I can go to look for more information about the random tree sampling you do? It's not mentioned in the original UMAP paper, and I had some trouble following the code that you provided for the tree sampling.
Yeah, let me go back to the slide. There's a reference at the bottom there, I think. Where are we? Yeah, Dasgupta and Freund, 2008 is the reference I think you want for that.